All right, welcome back. Today we're talking about linear functions. And the first thing to remember about linear functions is that first four letters there, we've got the word line. So linear functions are functions that make a line. We also have the word ear and the word fun, but we don't need to worry about those right now. Anyway, so linear functions, graphically, these guys make a straight line. So the graphs look like a straight line. Okay. So if we have a couple graphs, they could look like this, straight line going up at an angle, or it could go, it doesn't have to necessarily be at an angle. It could still go left to right if we wanted like kind of a horizontal line like that. Okay, so both those, they look like straight lines and they are in fact linear functions. Okay, so graphically these guys, just ask yourself, okay, does it look like a straight line? Yep, if yep, it's linear. Now, you're going to see two other types of problems, most likely. And one thing we need to recognize is that linear functions have a constant rate of change. Okay, linear functions have a constant rate of change. And what that means is it's related to what we call the slope. And if you've heard of that before, great, you are ahead of the game. If you haven't heard about it before, that's okay. You will hear about it in the next chapter. The easiest way is just to show you an example. It's pretty much your x's and your y's are going to be increasing at a constant pattern. Okay, so let me go like this. And then we've got a 3, a 5, and a 7. So kind of the most basic way to think about this is we got this xy table down here. Well, how do the x's change? What's the rate of change? To jump from a 1 to a 2, we plus 1. 1 plus 1 is 2. Does the rate of change continue? Is it constant? Well, 2 plus 1 is 3. So we can say these guys have the same rate of change on top. We plus 1 on both of them. Now the bottom ones, let's check the y's. This time we plus 2. And it's okay if your x's and your y's have a different rate of change. You just want to make sure the x's have the same rate of change and the y's have the same rate of change. So the y, we plus 2 on the bottom. 3 plus 2 is 5. Does that rate continue for here? 5 plus 2 is 7. So this would be a linear function. Why? Why is that? Because the x is increased by 1 and the y is increased by 2. And it's constant on the x's and it's also constant on the y's. Remember, these two guys don't have to be the same. Usually they're actually not. Anyway, let me show you one more. So we can just do one more xy table right here just for fun. And here we go. We've got 3, 5, 10, 7, 15, and 9, 20. Okay, so there's my input-output table. What I'm going to do is just go, okay, well, how do I jump from 3 to 5? What's the rate of change? Plus 2. All right, let's keep it going. 5 plus 2 is 7. Yep, and 7 plus 2 is 9. Okay, that's a 2. Let me get that better. That's a 2. Boop. So our rate of change in the x's is constant. On the bottom, we go plus 5 on the bottom. 10 plus 5 is 15. Yup, and 15 plus 5 is 20. There too, we can see constant rate of change happening in the x's as well as in the y's. Okay. Now, lastly, so we've talked about graphs. We've talked about rates of change and how you're going to have to see them in or have to identify a linear function if you're given an input-output table. You might also be given equations. So I just want to go over these real quick. We will go over them more throughout the year for sure. But quick deal, linear equations, these guys are your basic looking equations. They don't have exponents. They don't have square roots. They don't have variables in the denominator. Okay. A few examples. We've got like y equals 3x. Looks pretty standard. X equals 2. Yup. Y equals 7. Again, these guys are nothing fancy. Y equals negative 8x plus 2. Looks kind of fancier than the other ones, but it's still nothing terribly complex. These guys are all examples of linear functions. With linear functions, it's usually if you can either kind of simplify it so that you have a situation like this, looking a little bit ahead of us. If you've seen y equals mx plus b before, that is a linear function. And again, these guys don't have exponents, they don't have square roots, and they don't have variables in the denominator. Now, nonlinear functions, like you might think, okay, linear means line, nonlinear is not like a line. So we're going to give a few examples of these guys. And the easiest way to think about the graphs is that the graphs are not like a line. So if we've got our graph, our little xy axis right here, a graph that bounces like that is not a line, not a function. I'm sorry, it's not. It's a nonlinear function. It is a function, but it's a nonlinear function. We know it's a function because it still would pass the vertical line test, if you guys remember that from yesterday or 2 days ago. And another example, this guy, we call it a parabola. That is also a nonlinear function. And we do see things like this, especially with rates of increases and whatnot, but they're not linear. They're more advanced. We will get into them more in the second semester. So you can look forward to that. Now, all nonlinear functions also have no constant rate of change. So we have our XY table. 1, 3, 5, 7. And we got 2, 9, 20, 35. Okay. So we look at our rates of change here and we go plus 2, plus 2, plus 2. Okie dokie. The bottom, the top looks good. The bottom increases by plus 7. Then it increases by plus 11. Then it increases by plus 15. And you see the increases by 4 each time down here. That is not constant. Okay? This is not a linear function. And last but not least, one thing to add about this one. You could even have these guys double, like if the rate of change was plus 1, plus 2, plus 4. You can see a double pattern, but a double pattern would still not be linear. That would be a nonlinear function. Your constant rate of change has to be addition or subtraction. Hopping back to here, my last thing. What do nonlinear equations look like? Well, these guys are your complicated guys. So these guys have exponents. They have square roots. And honestly, they're just more complex. For example, y equals 2 over x. Oh, more complex, I should have added. You can have variables in the denominator for nonlinear functions. Y equals x squared has exponents. Y equals 5 to the x power. Or even something wild like y equals the quantity x plus 8 times the quantity x minus 1. And again, does it look complicated? Yup. Good news. We will be doing some of these problems later in the year. So again, look forward to that. But for now, the only thing we have to know is, okay, these are nonlinear equations. They don't look normal, and that's okay. They don't look like anything you've seen so far. And again, that's okay. All right. That's all we got for today. Thanks for watching, and